All right, so today we're doing review. So let's just start off with the first problem. So balancing an equation in basic solution. How are we doing on this one? Do we need more time or? So kind of walk me through, so what are our two half reactions? Who's getting oxidized, who's getting reduced here? So cobalt's getting reduced, so let's write that. So we have our cobalt hydroxide, and we can see it starts off in the 2+ oxidation state and then goes to 0. Okay, so it gained electrons. And then we have our oxidation side of it. So we started with sulfite. So going off of oxygen being -2, what's our oxidation state of sulfur then initially? Did you say +4? So right, we have -2 times 3, so -6, overall -2 charge. So it started at +4 and then ended at 6+. All right, so then we can just go through our steps. And again, right, maybe you have those notes handy of what we do. So of course, just balancing out our other atoms. So I'm going to start off with cobalt. So cobalt is balanced. And then let's balance our oxygens out with some water. So we have 2 oxygens. So adding 2 equivalents of water. And then, okay, balance out our hydrogens. So 2 hydrogens, 4 hydrogens. So now I need 2 hydrogens. Except now we're in basic conditions, right? So we have to neutralize our hydrogens. So if this has been acidic, we could have stopped here. And so we'll say because basic, add OH. So now we add hydroxide to both sides to neutralize it. And now those waters can cancel. So leaving us with our 1/2 reaction here. And let's put in our electrons. I neglected our electrons. So right, we said it went from 2+ to 0. So that's a 2 electron process there. And it's applying the electrons. Or excuse me, it's gaining the electrons. So we'll put the electrons on our product side. So now just a reactant side. All right, so there's 1/2 reaction. Questions about that half? So then now we just have to repeat with our sulfate. So, okay, now we have to balance it. So we're off on the oxygens again. So let's add water. And again, 2 electron process, so that's kind of easy, but we can add the electrons at the end. So now plus H2O. So just kind of repeat the process, right? So now I have to add 2 hydrogens. Now neutralize. Now back down to 1 water, so let's see. So then we have our sulfite plus 2 equivalents of hydroxide gives us H2O, sulfate, and then our 2 electrons. So does that look good for our 2 half reactions? And so now we can just finish balancing by electrons, but in this case, right, they were both 2 electron processes, so that was kind of nice. We don't have to do anything additional. And so now we could write our overall reaction. So now just writing, so cobalt hydroxide plus 2 electrons plus our sulfite plus 2 hydroxides just making sure I didn't screw up, and then plus cobalt plus 2 hydroxide. So now looks like hydroxide can cancel at the end. 2 electrons on each side. So again, just kind of making sure that it cancels out. And so it looks like we're left with cobalt hydroxide plus our sulfite gives us H2O and sulfate plus cobalt. Questions on that one? Does that look okay there? Make sure I didn't make any mistakes either. Questions, comments? So let's try another problem. So on your exam, you should have one like this. And so then you'll also have a problem on your exam similar to this one. I can't remember if we touched on this case specifically in class, but you should kind of have all the knowledge to accomplish it. And so I gave you the KSP values, and that was lacking from this problem. And so see if you can think about how to approach it. And so the key concepts that you're thinking about is, okay, you have your KSP, and then it wants it in grams per liter, and then we're at a solution that's buffered at a particular pH, so that'll be the key on your exam. And so in this case, we're looking at pH of 8.5. So just what does that mean for our rice table? So I'll let y'all start that before we go over it. All right, so let's see how it's coming along. And so you want to just start off with, of course, your rice table. So magnesium hydroxide, dissociating to magnesium, and then 2 equivalents of hydroxide. So again, on your exam, just pay attention to the compound and how many equivalents of hydroxide are being produced. Okay, so now we can set up, right, our KSP, so trying to figure out our solubility. So we have some sort of S, right, is going to dissociate to S and 2S. And don't forget, right, KSP then is going to be whatever our magnesium is times our hydroxide concentration squared. All right, and then what do we do about this pH, though? So what is it telling us? We can even think kind of more simply, right? So is this a basic or acidic solution? Basic, right? So let's figure out how much hydroxide is in there competing, right? And so we can do that by a couple of different ways. I'd probably just convert to POH, and then remember that we can get our hydroxide concentration then is equal to 10 to the power of the negative POH. And, you know, again, you could have solved the H plus concentration first, then gotten hydroxide as well. So let's do that. So 14 minus 8.5. So that gives us, right, again, our POH. I'll just write that. So our POH is 5.5 then. And so now let's take 10 to the power of that to, again, get our hydroxide concentration. And so now we can kind of add this in. So, right, this is our reaction. Now for our kind of initial conditions, right, we don't have anything in solution yet, but yes, we are at this pH, and so we just calculated again the concentration of our hydroxide to be so. So let's add that for our initial conditions. So 3.16 times 10 to the negative 6 here. Okay. And so then our equilibrium, or kind of, so equilibrium change position. So then, right, this will still be S, but then our hydroxide, right, will be 2S plus our initial concentration. And so now you can kind of see where this is going. So now we can plug this into our KSP expression. And so now we just have S for magnesium times 2S plus 3.16 times 10 to the negative 6 squared equals our KSP, so 5.6 times 10 to the negative 12. And so now we can probably make some assumptions at this point. So, right, obviously this would be kind of difficult to solve. You could try to distribute this out, but we can probably make a 5% assumption, or less than 5%. Again, just judging off of this negative 12, and then this is negative 6. So we can get rid of this 2S factor, right, since this is much, much greater. And we'll double check our assumption, but so now this will make it much easier to solve. So let me just plug that in. So 5.6 times 10 to the negative 12 divided by this squared. And so now I get this for our value of S. That seems high to me. Just making sure I didn't mess up the algebra. I guess that works out though, because that would be negative 12, so that does kind of cancel. But then our S is very large. Yeah, so I don't know if we can actually make our assumption then, right? Because do you get that for S? Yeah, then S would be too large. So now I think we have to, this is perhaps not the best example. So on your exam, this number will be smaller so that this will work out. Because otherwise, I don't think our assumption works out that great. I was just going to ask Wolfram Alpha. Come on. So let's see if this will solve it. So if we do x, 2x plus 3.16. Please read this correctly. Yeah, so apparently we actually couldn't make an assumption for that, so just plugging into a calculator, so I'm just getting a different answer. So let's check that. So x is 1.06. So, oops, our assumption was probably wrong. And so again, I'll just say plugged into calculator for now. Otherwise, we'll have to, we can go through this algebra, but like I'm telling you on your exam, these numbers actually will work. So I'll say plug into calculator for now. And so then I just want to double check our value. So 1.06 times 10 to the negative 6 for our S. And so now I'm just double checking our solubility into here, since that was, again, actually on the order of our value, so apologize for that. So now plus, times 2. So I'm just replugging it into here right now, double checking that our calculator gave us the correct value. So 3.16. So then this squared times 1.06. Oh, why is everything off today? What did I do wrong? So let me plug that. Plus 2. That's squared. I just don't know how it's so off. Well, that's frustrating. Oh. All right, now it's algebra time. This is not really where I wanted to go with this sample problem. This is what happens when you try to pick a new sample problem, then the math doesn't work out if you didn't test it fully. All right, so obviously we have to brute force it, and I don't know why all the calculators are failing. And that look correct. What it interpreted. That's strange, but now I don't trust it. So then we'd have to do algebra. All right, let's skip this because this is not what the point of this exercise was. So I don't know if we'll have to redo it with another example that's actually on the correct order of magnitude. So I apologize. I don't want to waste more time with it because the algebra is not relevant. All right, so let's just switch gears to another type of problem on your test. So now a reaction has a delta H of 320 kilojoules per mole and a delta entropy of 101 joules per mole. So at what temperature does it become spontaneous? All right, do we have an answer for this one? Or I guess let's start with what formula do we need? So delta G equals our change in enthalpy minus T delta S. I assume that one, right? And then, again, the main thing to watch out for was you have this kilojoules versus joules. So again, however you want to treat that, either multiplying this by 1,000 or dividing this by 1,000, either way. So we kept it in kilojoules, so 320 minus our temperature times 0.101. So what do we get for our temperature? So 3,168, and so I think people got that as well. All right, and then I was gonna, jump back to this one, because I realized what I did incorrectly. I didn't put the square when I put it into the calculator, so that made a big oopsie. So that's supposed to be the answer, but like I said, the work will be such that you can make the assumption. And this was a horrible example, obviously. So that's, again, oh, geez. Okay, obviously I'm just incompetent today, apparently. Okay, so once you actually plug it into the calculator, oh, come on, now I lost my answer. Perfect. So this was the correct answer. So our S equals 0.0001108, but that's, again, molar solubility. And I should have mentioned that it was asking it in grams per liter, so we'd still have to multiply by the molecular weight of our compound. But again, this problem is taking too much time. All right. Let's try another type of problem. So we have our R equals 8.314. I'll give that. That's our standard. And we're looking at this equation. Oops. So the dissociation of HF and so it says at 30 degrees Celsius, the dissociation of HF is 5.7 times 10 to the negative fourth. So what is the delta G then for this reaction? So again, formula cheat sheets are going to be helpful for this exam. Maybe you tab your textbook too of relevant formulas or rewrite them. Sorry, delta G. Sorry. do we have, what's the formula that we need for this one? So excellent, so we have our formula, and then you were given R in this case, but again, energy, and then T, of course, in Kelvin, so then we're good to plug in everything. So our T should be 303 for Kelvin times natural log of K. And so what do we get for our delta G then? So 18,817, so I assume that's joules. And then we could also convert it to kilojoules. So 18.8 kilojoules, whatever unit. All right, let's look at some oxidation states. So if we have this compound, determine the oxidation state. And determine the oxidation state for this organic structure. And this is just one like vertex here. It's not very good at drawing. Pentagram thing. Pentagon. So how are these coming along? So what do we get for the oxidation state? So let's just start with the easy ones. So what do we get for our chlorine over here? So -1. So yeah. So right, don't overthink your easy halogens. And then so same thing with bromine. What should it be? So still -1. And so based off of these, then, what oxidation state is our vanadium in? So check that, because, right, it's overall -2. And then, so then add up, right, -1 times 3 plus -1 times 4. So it looks like we're at -7 overall for the chlorine and the bromine. So then what does vanadium have to be? So 5, so +5. Excellent. So this is kind of a weird one. I was about to say that. So the way it's written in, so we haven't gotten this far in like transition metal chemistry, but like for our purposes, right, we can just add up the charges. But really how to look at this is that these are bound. So we have some sort of vanadium chloride complex. But it's missing electrons or something. So then we have, right, this, and then your bromines are floating around as your counter ions. So they're actually outer sphere, right? So they're just like the ionic compound portion. So -4, right? 2 minus overall. So this has to have a 2+ charge somewhere. So this is 2+ then, right? This is -4. And so that's telling you the oxidation state too. So right, we have +5. And so that means, and we can look at our vanadium, right? So vanadium, again, kind of going beyond where we are, but we'll look that it's treated as a D5, so 2 electrons from the 4s, and then the other 3 from the 3d, but it effectively behaves as a 5 electron containing compound. 3 of those are involved in bonding, and then 2 of them flew off at some point, right, to give us this 2+ charge there. And then this may or may not be the correct geometry. I just kind of based it off of the Vesper structure. But again, we haven't gotten to transition metal chemistry, so then we'd have to look at other like ways to analyze it as well. But all right, and then how did this one go? And so I was kind of cruel and didn't show all these hydrogens, so you had to remember to fill those in. And so kind of depending how you wanted to analyze it, so I'd probably just start at each carbon. And again, right, the hydrogens are usually +1 since we pull them off. And then they would get no electrons from this bond, so leaving them as 1+. Remember, all the carbons split equally. So this is -1 for carbon, -1. So this pattern kind of repeats, but then let's pause at these weird ones, right, where it's next to nitrogen. So, okay, nitrogen takes those 2 electrons, and then that leaves carbon with 1, 2, 3. So this one's a +1, right? And then now nitrogen, so we have nitrogen versus carbon again over here. So it takes all the electrons. So, And then this is also not drawn on here, but we also should think about, right, our lone pairs on our nitrogen. There's also technically, right, lone pairs on our sulfur that aren't drawn. So then, okay, we pull it off, and then it gets 1, 2, 3, 4, 5, 6, 7, 8. So then that gives it a -3 oxidation state. So then let's look at these other funny carbons. So we have this carbon here. So again, splits evenly. So it has 1, 2, 3, but then it loses out right to the sulfur. So this also has a +1 oxidation state. Okay, finishing up with sulfur. So sulfur again gets all the electrons. So -2, right? It has 1, 2, 3, 4, 5, 6, 7, 8. And then leaving it -2 formal charge. So now this carbon has lost out to everybody, right? It's next to sulfur, sulfur, and nitrogen. So it has 0 electrons on it, so this is +4. And then hydrogen's +1 again, and then this sulfur is going to be -2, just repeating the pattern. So again, sulfur should have 2 lone pairs, gains all of those. And then double check yourself, right? Add up everything. So those cancel, so you can quickly cancel out kind of those, but now we have to do some adding. So 2 + 2, so that cancels out. So +2, -2, and then making sure the last cancels out. So we have +5, -5, so again, overall neutral. Questions on this one, especially the organic structure? So I think the one in your exam should be a little easier, the organic structure. And I did draw out the lone pairs explicitly on your exam as well, so that should help. All right, let's take a quick break. So we'll take our 10-minute break and then do some more review problems.
I guess my question or concern is coming to the conclusion that chlorine is going to be makes sense to me. The main thing is 5, but just like going through the set of rules, that's going to stop it. What rules goes having oxidation? How do you get to that -1?
It's just because they're the halogens, right? Because usually you assume the halogens are -1. It's only when they're like in covalent compounds, especially with like themselves, like I think IF3 would be like a major example. So then for IF3, you would assume those 3 fluorines are -1, and then you can base the iodine off of that, for example.
So they're typically
Yeah. Yeah, exactly. Yeah, so they're basically like oxygen, right? Where like oxygen is almost always -2, unless it's a peroxide. So same thing with the halogens. They're always -1.
So in the book it says for rule 4, it says fluorine atoms and compounds are always inside an oxidation state.
Yeah.
Referring more to like halogens, because there's like exceptions, but
Right, so like if you have, again, going back to IF3, so that's where like fluorine, since it's the most electronegative, will take the -1 priority. And then, so then chlorine, bromine, and iodine would be based off of that, but yeah, those are only like halogen versus halogen usually, but you don't typically, yeah. Otherwise, like I said, if it's attached to a metal or aluminum, it's always that -1 oxidation state. So you can start looking at 30. I'm just going to run to the bathroom real quick. So what are our thoughts for this one?
I immediately thought it was you have a low pH, you have excess hydrogen, and hydrogen ions don't bond with oxygen with neutralize their charge. And HCO is going to be one that has a single acid that can be removed. And since hydrogen's highly reactive, it's series of
So that's good, but also like what we said about silvers, remember it's like one of those amphoteric species, the silver oxide right from the demo. So yeah, so this would be one where its solubility does increase. But then what about other ones? And maybe think about what these could be the conjugate base of.
amphoteric means it can be acidic or basic.
Yeah, yeah, so silver could be more soluble in both acidic and basic solutions. So that was from, like I said, the demo. But then the other ones potentially have a different thing to think about. and it may come up on the exam. So does this ring a bell? So it has this equilibrium. So it's from chromic acid, but it's a diprotic acid, right? So you can have one H plus, so then in acidic solution, right, you have this equilibrium. Sorry, let me write that a little better. So, right, we have our chromate, and so this can react in acidic conditions to give HC. Sorry, I was trying to put that into hydronium, H3O. So I was trying to find your acid base list. I don't know if that would be helpful. Because maybe people just like also weren't recognizing that that's chromic acid. So I was trying to find your reference sheet from winter quarter. Oh, that's annoying. So chromate's not on there. So the ones on your exam, I will say, will be ones that you are familiar with, but you do want to still, again, appreciate this example. So again, that's the problem with chemistry and pulling all these difficult examples, as maybe you didn't know about chromic acid, but that was the key in this one. And so, right, this is chromic acid, but like I said, on your exam, I'll pick stuff that you're more familiar with, you know, carbonates, hydrogen carbonates, stuff like that. So think about those and how they behave. So I'll just say think of carbonates and hydrogen carbonates, right, how those have equilibrium in solution, right? Those are kind of things you've seen before. So same sort of concept going on here. And so B, that's also, again, the same trick is, I believe this is oxalate. So this is another organic acid. Yeah, so this is oxalate, but like I said, maybe you weren't familiar with the acid form, so again, same thing. This is a conjugate base, so it makes HC2O4, and then can do that again to again make oxalate acid of H2C2O4. Yeah, unfortunately those weren't included in your sheets, but again, it's like impossible to have a perfect reference of every acid and everything. Oops. Not readily available, but I can print it out. All right, so let's try another one. And, so before we move on from this, right, other things to think about for solubility would be, right, the common ion effect. And so this could be asked, right, on your test, either again, like mathematically, kind of like we saw with my terrible example here, that, like I said, just didn't work out because we couldn't actually make the assumption, but right, same sort of thing. If you have a common ion, right, that tends to decrease your solubility. All right, so let's look at titrations now. And given the lack of titration labs people have turned in, I'm a little concerned. No. So yeah, we won't have a lab practicum this quarter though, because you're going to have your final presentations and your posters.
For the ticket,
Yeah.
what day is that?
It's probably on the syllabus, but it's probably week 10. But yeah, your syllabus has to be fixed because, like I said, the field trip is looking sadder and sadder since no one wants to respond to me. But yeah, which eventually we should take a vote on what we're doing. All right, so let's do some acid-base stuff. And so let's say, so we're doing a titration, and we have 20 mils of a 0.3 molar acetic acid solution. And I'll give you the Ka. So the Ka, at least what I have written down here, is 1.76 times 10 to the negative fifth. And so let's just start off with, and let's just say we'll titrate it. So with 0.15 molar of KOH, obviously a strong base. And so let's just start off with what is the initial pH? So prior to any addition, how would you solve that?
The negative log of the molarity.
So yeah, set it, because it's not just the negative log of the molarity though, right? Because it's a weak acid. So we have the Ka. So you could do the pKa, but I probably, because what are you trying to do? Because you're going to need to use a Rice table for the first one, right?
You're doing rice tables, so it's really different.
So let's see how this is going. So yeah, like you were saying, so we set up just our equilibrium, right, of what's going on. So we're disassociating into our conjugate base plus H plus, or hydronium, but just call it H plus. And so then, huh?
Maybe a
C
C after the picture.
after the A,
CH3
CH3,
on the left.
oh, COOH. So then, right, start with our molarities, so 0.300 molarity. And now figure out, right, how much disassociates. So we have plus x, for our change. So, sorry, let me slow down a little. So initial, right, just starting off with our initial concentration, and then, like I said, change. So plus x, and then this will be minus x. And then, of course, equilibrium. So 0.3 minus x, x. And so now we can set it equal, right, to our Ka expression. So now just x squared over 0.3 minus x is equal to 1.76 times 10 to the negative fifth. And so again, I'm hoping we can make an assumption here. So just getting rid of this minus x. So let's plug that in. So I get this for our x. I'm just checking. Okay, so 5% assumption is still good. So x equals 0.002297. Oops. And so again, this is equal to our H plus concentration. And so this is a good review, right? So good recap. So this is, again, right, what you should be doing for your lab. So this is just the initial pH, right? And then you have to set up your equilibrium. Now we actually figure out how much is disassociated. And so now we can just get, right, our negative log of H plus equals our pH. And so about a pH, initial pH of 2.64. Okay, is that what we all got there? Questions on that one?
What's the rules for the assuming less than 5%?
So once you get the x there, right, so basically you kind of judge it by the order of magnitude is the trick. And so I was kind of saying, all right, there's a large enough difference in our order of magnitude where we can make that assumption. And then you just check it. So once you get x, right, then you plug it back in for this, wherever you made the assumption. So since we're comparing it to our original amount, right, I just double checked it real quick, comparing it to the 0.3, making sure that it's less than 5% change. Because otherwise, if it's greater, then you can't make the assumption, and then we got to redo it, right, with,
Or,
Yeah, I was confused about that too. I don't understand why you get rid of the x in the denominator, but not the numerator.
because we need it in the top, or else, right, then we'll get nothing. But we get rid of it in the bottom, right, because we're just comparing it to the change in the 0.3. So we're saying that this change is so insignificant, right, that it'll still be 0.3, but then we need the x squared, right, to solve for something. So we can't just, like, get rid of everything, right? You're comparing it to something. Yeah.
it's the Ka's magnitude that you're determining that 5%, right? Or the
Well,
K's.
yeah, so it kind of helps, right? But like I said, we still got to check it. And going back to this example, right, I made the incorrect assumption that that was small enough, but that's why it's like, oops, once we get the value out, you plug it in, you test it, and then you're like, wait, I couldn't actually do that. And then, Kaden, did you?
How likely is it that we'll, on the exam, we'll have one that, like, we can't really have 5%
If you will be able to make the assumption on the exam, yeah.
Thank you.
All right, so then that's this part. And so now let's just do, I'm just kind of walking through the exam question. And so now let's just determine the volume of KOH at the equivalence point. So remember, what does that mean by definition? Don't overcomplicate stuff. It's my biggest advice.
The equivalence point is the point where the number of moles between the two are equal.
Yeah, so good. So I'll write that down as a hint then, right? So basically, our moles of acid equals moles of base. So go ahead and finish those calculations, right? When is that?
Does it matter if it's a weak acid or strong acid?
No, so that's the point of the equivalence point at least, right? And so especially if it's just determining how much volume, right, we just care that the moles are equal. So it doesn't matter whether it's strong, whether it's weak. And then, yeah, the only weird thing is calculating the pH, obviously.
Are we going to have any multi-product acids in the
I don't believe so, at least not, yeah, not determining equilibrium. So do we have an answer for this one? So 40, is that what other people get? So we could, again, just walk through it really quickly. So, right, figuring out how many moles of acetic acid we have. So I'm just going to multiply 0.3, right, our moles, our molarity, so moles over liter, multiplied by, and I know some people like to work in millimoles, that's fine. I like to just convert everything back to liters or else I'll be confused. So then we have our 6 millimoles there total of our acetic acid, right? So then we're asking, so how many milliliters or liters of KOH do we need? And we only had a 0.15 molar solution. So 0.15 moles per liter. So So then if I want 6 moles, so then divide, so then we get, just like you said, 40 milliliters. Does that sound good to everybody? From our molarity, so right, we were given initially that we have a 0.15 molar solution, and then we can just plug that back in, so 0.15 times 0.04, so get us back to 6 millimoles again. All right, so that looks good. And so now let's do kind of 2 types of problems. Again, on your exam here. So let's just try, so calculate the pH then after the addition of, and let's do 12 milliliters of KOH. So kind of how would you approach this, right? What's kind of the easier way? Some people brought up pKa's earlier, so now would be the time to use that. So just think about how you're going to set it up. Yeah, so we're still working with the same conditions, right? So we still have.
We're assuming no addition prior pH.
Correct. So yeah, you're just saying that we've added in 12 milliliters total of KOH, right? So now what's the pH? And so just kind of a reminder, right, we're before our equivalence point, so this is a good situation to use our Henderson-Hasselbalch now, right? The pKa, or, sorry, pH is equal to pKa plus my log base over acid, right? So we're figuring out how much conjugate base we're making, how much acid is left over, and so I would just convert everything to moles, and so just double check me. So we have, again, our 0.3 molar solution, 20 mils of it. So starting off with 6 millimoles of our acetic acid, right? And then calculate how many moles of KOH you have. And, you know, kind of depending how you want to look at it, I just kind of have our initial, right, again, moles before you do the reaction. And so we said we had a 0.15 molar solution, so times 12 milliliters, right? So we started off with 0.0018 moles of KOH. Again, let me know if something seems funny. And so then, right, do the reaction / equilibrium. And so now we're just subtracting. And again, right, if you haven't done your lab still, this is how to approach it prior to our equilibrium. So figuring out how many moles remain. Obviously this gets consumed, our hydroxide, but then we make this many moles of our base, right? And technically we should think about our total volume, but again, it's going to cancel out, right, when we divide it. But again, I just like to keep it in mind for other purposes, such as like the last situation where the total volume will be relevant. And so let me get, so the pKa is just the negative log of our Ka. And so now I have roughly 4.75 plus my log of, again, base over acid, so 0.0018 over 0.0042 moles. Again, volume cancels, so we don't need to make a molarity adjustment. Oops. So do we get this for the pH? So I see some agreement. So 4.3, I'll round it to 3.9 there for our pH. All right, so that looks good. And so now let's try the last sort of situation that we'll see on our exam. And so again, right, at least you calculated the equivalence point. And so now what happens, so calculate pH after 45 milliliters of KOH are added. So what's the difference? How do you treat that? It's a little bit different. So I'll kind of write that as a hint as people keep working on it, right? So basically, all acid is consumed. So you're trying to figure out essentially how much hydroxide is left. And this is where I said, you know, the new volume will matter for a concentration. So I'll let you finish working that out, or at least trying to. And again, right, keep in mind that you started with 20 mils of acetic acid, because you at least need to know the total volume.
Start coming.
I think it was 20 mils of acetic. I'll have to look.
This is example 2.
So yeah, start walking me through it, but essentially we could kind of start similar to this setup, right? But then it's gonna kind of just turn into a hydroxide problem. And, or maybe, you know, you just want to kind of figure out your moles of each. But again, we can think about our reaction. Okay, plus KOH gives us our base. And water. And so like I said, we had 6 millimoles. So we already calculated that. But then if we have, so 45 milliliters, it was a 0.15 molar solution. And so this is kind of the key, is past the equivalence point. Well, now we have more moles, right, of base than acid. And so maybe you start off like this and then kind of do the reaction. So, right, react. Well, obviously all these are going to be consumed. And so now we're left with 0.75 millimoles. So minus 0.006, oops. And then, so I was saying, right, that we need to keep track of our total volume. So again, right, we need our POH is equal to, again, our negative log of hydroxide concentration. So now we can just focus on calculating that, since again, right, all this was consumed. So now it's just a hydroxide problem.
Does the conjugate base factor in the role?
No, not anymore. Yeah. So like I said, once you're past the equivalence point, the conjugate base is not really driving much of it. So it's only relevant at the equivalence point. That being said, on the exam, I'm not making you calculate the pH at the equivalence point. But for your lab, right, that's where you want to figure out the KB and do equilibrium, just like in your homework. But here, let's just figure out our concentration of hydroxide. So just converting it back to moles over liters. So that's why I was saying now it does matter our total volume. So we had 45 plus 20. So 65. And so now I'm just plugging it in properly. So 0.065, so converting back to moles and liters. And so now this is hopefully my correct molarity. Again, just double check me on my math here. So 1. So is this what we get for our hydroxide concentration? And so then we can plug it into our just POH formula. So there's our POH, and then of course we need to do 14 minus that. And since we are past the equivalence point, right, I would expect it to be pretty basic. So 12.06 for our pH there. All right, I think we've hit up most of the problems. Other things that you'll have to do for your exam. So I haven't decided whether I'm going to modify your exam or not. I was going to put multiple choice questions, but I haven't, so I don't know. It may remain as it is. As it is, it's all free response. So yeah, let me go over what you have. So you have your first question is determining solubilities of a certain substance, right? What happens based on common ion effect or pH effect, something like that. Number 2 is evaluating when a process will or will not be spontaneous. So probably you want to look at that Gibbs free energy chart. So just kind of verbally and symbolically kind of understand what that means. And then they'll be determining oxidation states. So just like we did with these practice problems, there will be a buffer solution one. That's just calculating pH, which I think you can do because that's Henderson-Hasselbalch. There's going to be obviously a balancing, some sort of redox equation. There's going to be the titration one, just like we did, so one very similar. There's going to be one, like I said, that will be just like this one, except the solubility will be way less, so that you can make an assumption. But again, just still with the pH dependence. You'll have this type of reaction. You'll have this type of problem, since we went over it. And then the last bit will just be like identifying oxidizing or reducing agents. And so that will be a skill. So identifying, oxidation, reduction, or the agent. So if it underwent reduction, right, oxidizing agent. So like I said, right now it's at 10, basically free response. I guess the last one is technically a multiple choice question, but. Yeah, we basically went over most of the representative problems today. Any other questions? And then is anyone doing lab makeup today? I didn't get emails from people officially. I know other people were trying to do other dates, which is fine. Just let me know, like I said, like right now if you're doing the lab today so they can set up. Otherwise, if you're trying to do other times, just email me because I'm starting to lose track of like who's doing what. And then, just a reminder, right, so the Thursday people that I miss will do it on Thursday, if that's fine, so after the exam. Yeah, I think that's all I have. So good luck, study, open notes, have all your formulas, have your scenarios straight for your pH calculations. Yeah, I need to give yours back or finish looking at it. I just don't have them like on me at the moment, if you wanted to wait a little bit, but otherwise I'll try to hand them back on Thursday. Hmm?
They'll just have it in class to hand out.
Yeah, well, I'll hand back stuff on Thursday. That was kind of my plan.